So now we are continuing with the previous video, that video in which I told you what is the void relation, that is empty relation. Then I told you universal relation. Then I told you identity relation. Then I told you reflexive relation. Then I told you symmetric relation. In first relation, that was void relation, I told you phi is an empty set, or phi is a subset of A cross A, so it will be a empty relation. Then I told you A cross A itself will be a subset of A cross A, that means it will be a universal relation. Then I told you identity relation, each and every element must relate with itself. That only if that condition comes, we will say the relation is said to be identity. Then we have done that if each and every element of set A relate with itself, only I am not putting. If each and every element of set A relate with itself, we will say it will be uh, reflexive relation. Then we have done the symmetric relation. In the symmetric, I told you if A and B are the two elements in the set A, if they are related, their reverse must be there. Now coming on transitive relation, what it says, a relation R is said to be transitive. A relation R is said to be transitive if and only if AB is a member of R, means A relates with B is here. You can write this way also. A relates B. You can write this way also. You can write this way, or AB is a order pair member of relation set. A relates B, and is this symbol. This is symbol for and B relates with C. BC belongs to R. If A relates with B, B relates with C, implies A relates with C. For all A, B, C belongs to A. If this condition hold, we will say yes, relation is transitive. For example, if I'll start with this 1, 1, 2, 2, 3, 3. What relation? Identity. Then I'll take 1, 2. Then it will be called as, first was identity, then it is reflexive. Then if I say 1, 2 is there, then 2, 1 is also there if I am putting, that will be called as symmetric relation. By the way, now we have 1 related with 2 and 2 relate with 3. Then 1, 3 if also there. Then we will say yes, it will be a transitive relation. Transitive relation is saying what? 1 relates with 2, 2 relates with 3, then 1 relates with 3 is here. So if this condition hold, we will say every pair which whatever present here will hold this condition, that A relates with B, B relates with C, then A and C must relate, then it will be called as transitive relation. So here in this case, if I say what kind of relation it is, reflexive, yes, it is reflexive relation. Is it symmetric? Anyone can tell, is it symmetric? No. Why it is not symmetric? Because 1, 2, 2, 1 is there. But 2, 3 does not have 3, 2. This is missing. 1, 3 is there, but 3, 1 is missing. So that's why you can't say this is symmetric. No. But what about transitive? Transitive, when you take any pair, 1 relates with 2, 2 relates with 3, automatically 1 relates with 3. We are getting it. Any other one? Just check. 2, 1, 1, 3. 2 relates with 1, 1 relates with 3. Then 2 and 3 are related? Yes, it is also there. So we will say yes, it will be transitive relation. So here we will have 3 relations. One is reflexive, symmetric, and transitive. These are the 3 relations now we are combining and just naming it another relation. So now we are coming on the next part, a relation, that is equivalence relation. So next is equivalence relation. Equivalence relation. So next relation is equivalence. So the new relation is equivalence relation. What the equivalence relation says, a relation R a relation R on set A is said to be equivalence relation if and only if first R is reflexive. That is what I have to show. R is reflexive. That means we will say A and A belongs to R for all A belongs to A. Second condition is R is symmetric. R is symmetric. That is what condition I should have. A B belongs to R implies B A belongs to R for all A and B belongs to A. And third condition is R is transitive. What that is? That shows AB belongs to R and at the same time BC belongs to R implies AC belongs to R for all ABC belongs to A. If these three conditions any relation satisfies, hence what you should say relation come out to be equivalence. And we will be having question on 4 marks or 6 marks on this. One relation they will define and they will ask on one set A and they will ask whether the relation is equivalence or not, we should find out. So whenever they say relation you have to prove equivalence means I have to prove that each and every element relate with itself, that is reflexive. Second one, if A and B relate then BA is also related, that means order pair in reverse must be there. And third says that if A relate with B, B relate with C, then A and C must be related. So if these three conditions you satisfy, this relation is called as equivalence relation. Is this clear? Here in this case, reflexive I told you, A belongs to R, every A relate with itself. This is must condition. R is symmetric, if A and B are related, then B and must be related. R is transitive, that is AB belongs to R, then BC belongs to R, then AC belongs to R. If these condition any relation satisfies, we will say it is equivalence relation. Now I'll be taking examples or the questions. Now keep in mind in this question, the writing is very important. If you are missing some steps, you want to write down directly, you are not getting marks. So in this case, this is the part in which all the steps are important. So everything you should write in this chapter. And 4 marks or 6 marks, anything they can give. Earlier we used to have 6 marks question on the relation. But as there is a pattern change, 6 marks question has reduced. So maybe it will be this time 4 marks question. So that you should keep in mind. Now we are taking examples on equivalence relation. So write down first example we'll take now. So first example is, let R be a relation on the set of all lines in a plane. For example, this board is a plane. And if board is a plane, or you take this as a circle, this is the plane we have. In this, whatever the possible lines you can draw, we are taking them. This is the collection of all the lines. And let this set be denoted by capital L. So capital L be the set of all the possible lines in a plane. First thing is clear. Now it says, and the relation which we are going to define is such a way that L1 and L2, two lines are said to be related. Two lines L1 and L2 are said to be related if these lines are parallel. Here in this case you are finding this line is coming parallel to it. So in this case this is L1 and this line is L2, then they are related. These two are not parallel, so they are not related. These two are not parallel, they are related. So many possibilities are there. One more line is here. This is parallel to this is parallel to this. So I say this is L3. So L1, L3 will be related, L2, L3 will be related, L1, L3 will be related. So infinite many parallel lines are there. So we can just get the parallel condition. So now we are we have to prove that this relation is equivalence. For that, first we should show that it is reflexive. Please note the steps you should not miss. I want that In reflexive, each and every line must relate with itself. So in this case, what we have to show that L1 relate with L1, L2 relate with L2, L3 relate with L3. Is it possible? L1, L1, are they coinciding lines? Yes. If they are coinciding, means can be counted as parallel lines. So what I do here, let L is some line we have taken, belongs to set A, L. Then we know, this is a known condition to us. What that is? L is parallel to L. Nothing new. We know that L is parallel to L. And if L is parallel to L, what does it mean? If L is parallel, L1 parallel to L2, it will be related. If they are related, they are parallel. So as we have L parallel to L, what does it mean? This implies L comma L belongs to R. For all L belongs to L. As every line is parallel to itself, that means every line is related to itself, or L belongs to R. Or you can write this also. L relates with L for all L belongs to L. You can write this also. Either you write this or you write this, that is one and the same. So first thing we have proved. So in this case, after getting this, therefore, R is reflexive on L. R is the relation which is reflexive on L. L means the set of all possible lines. Now coming on second part. This is the reflexive we have proved. We have proved that each and every element relate with itself. Now we are coming on symmetric. Symmetric means if L1, L2 are related, L2, L1 are related. We can do that also. Now we are coming on second part, symmetric relation. In symmetric, we will be taking two members. So let L1 and L2 belongs to L. And we are taking these two such a way that they are parallel. Or I should say such that L1 and L2 belongs to R. First we have taken any two members, because I told you if 1, 2 is there, then 2, 1 must be there. So first we have taken 1 and 2 is there, then we should prove 2 and 1. So here we are taking L1 and L2 are two lines such a way that they are related. If they are related, what does it mean? L1 will come parallel to L2. As they are related, we will say L1 is parallel to L2. If L1 is parallel to L2, automatically I can write L2 is parallel to L1. L1 is parallel to L2, what does it mean? L2 is parallel to L1. And if L2 is parallel to L1, what I should say? L2, L1 belongs to R. Because L2, L1 parallel, that means they are related. What we have proved? L1, L2 are member of R. We have proved L2, L1 belongs to R. For all L1, L2 belongs to A. Therefore, what I should write in this case? R is symmetric on A. R is symmetric on A. On A, this will be L. Then coming on transitive. Next relation is, next type we have to prove, that is transitive. So now in transitive relation. In transitive, we will be having three members. A relate with B, B relate with C, then A and C must relate. So we will start with this. Let L1, L2, L3 belongs to L. Such that, what condition I am taking? L1 and L2 belongs to R. These two are related. At the same time, L2 and L3 are related. If you have this condition, what I should say, L1 become parallel to L2. And at the same time, L2 is parallel to L3. One thing you should keep in mind, if the line L1 is parallel to L2, at the same time L2 is parallel to L3, then automatically L1 and L3 will be parallel. Definitely, yes. So L1 is parallel to L3. And if L1 is parallel to L3, what it indicate? L1, L3 belongs to R. For all L1, L2, L3 belongs to set L. all L1, L2, L3, we got this condition that if L1 or L2 are related, L2 and L3 related, then L1 and L3 related. So therefore, what I should say finally, what I should say, R is transitive on L. And finally, what I am going to write here, as the relation is reflexive, as relation is reflexive, symmetric, and transitive. So R is equivalence relation. Hence proved. So this is the first question you have, which we have completed. Please go through thoroughly, and then we will be coming on next question. So these type of questions they will be asking. They will be simply giving exam questions to you, and they will ask equivalence relation you prove. So first kind of question will be in which they will be simply asking you prove that they are equivalence relations. Okay, next video will continue.